Okay. So Brandon asked for me to talk about other stuff, and I have to confess that at first I said sure, because I knew exactly the talks to give, as I have a few in the can, and so I thought, oh, okay, I'll talk about particle physics and cosmology and the connection between them. But of course, I'm sort of realized yesterday as I was pulling that together that in fact I wasn't really quite sure what talk to give to this group, because I think some of you know more about some of this stuff than I do, and some of you maybe introductory. So I'm not quite sure what to do. So I'm sort of thinking the story that I like to tell that's very exciting to me is basically what we're doing in particle physics and the evolution of particle physics, and then how sort of a similar parallel story about cosmology, and then the realization that these two tie very much together in the Big Bang, and how what we are today sort of evolves from the physics of the very small, very long ago. Okay, and I know for at least a couple of you that you've seen this particular story before from me, and probably other places. I can jump ahead a little bit. A lot of what's exciting these days is not so much Big Bang, but the fact that the Big Bang is actually got real problems, and to fix it you have to invoke something called inflation, which is a pretty wacky idea. And once you do that, it's really hard not to have multiple universes come out of it. And so I just wrote a book on all of this, which I'll advertise to you later, because it's actually written at a level that it was designed for non-experts, in part because I am non-expert on it, and I tried to make it very accessible, so you may in fact have students that might suggest it. So anyway, I'm happy to jump into this, or it should be very informal. So just ask what you want, or if I'm boring you because you've seen all this stuff before, then we can move on to the other stuff where maybe you haven't seen so much. So anyway, for me, the whole idea of particle physics comes together because we have this great idea of the atom that comes out of Rutherford scattering, where you shoot, where you take an alpha source and the charged alpha particles go through this thin gold foil, and in the initial ideas of the atom, it's sort of this plum pudding model. You have a diffuse positive charge with some negative charges mixed in, because all you really know is you've got some positive stuff that comes out, some negative stuff that comes out. So how do you try to hold it together? And so the initial models of atom are like that, and then if you have a positive particle going through a foil made up of things like that, you expect it to sort of go through with small deflections. And in fact, that's what you see, except now and then the thing comes straight back at you. And so Rutherford described it as a 15-inch cannon shell basically being deflected by some paper, right, a sheet of paper. And in order to explain that, you have to put all the positive charge in a really small region, about 10 to the minus 15 meters in size, and you can do the kinematics and convince yourself that it's there. But then you've got a real problem, because you can calculate very quickly the Coulomb charge between all the positive particles that you know are in the atom, and you realize that if I have all this stuff in there, it's got to be blowing apart. So just straight up, you know there has to be something new involved, and the problem is you can't really get in there to figure out what's doing it. You can't just look so easily. So the analogy I like to use is, imagine that that you wanted to figure out how to make a car, how a car works, but you couldn't actually open the hood and look inside. And one of the things you could do is, if you had a lot of, actually you guys could really do it, you get the teenage boys in your high school you give them each a race car and have them drive around and crash into one another. You give them helmets and stuff. You know, they got airbags, but they go wow, I didn't realize I had a soundtrack. I don't know what kind of, I guess normally I give the talk and I don't bother hooking up the sound. So I'm going to get surprised on here. Anyway, so if you have enough different types of cars and you crash them into one another and you start looking at the pieces that come out, you can begin to notice patterns. So you'll notice that they all have spark plugs, but only certain cars have Volvo emblems and things like that. And you can do this at different energies. And after a while, you can begin to ferret out, if you do it with enough different types of cars and trucks and stuff, you begin to determine what's essential in making a car work. And so that's basically what particle physics was doing in the last, from the 1930s up through the 1980s. That's more or less what we did. And instead of cars, we use these accelerators, and this is Fermilab, which is now outdated. It was the highest energy accelerator in the world until about last year or year before, when the LHC turned on. And so the idea is to send particles around, smash them into one another, and look at them, and then we reconstruct them using these large detectors. And again, at the LHC, we have things that are about 10 times this size, but these are big enough projects, large collaboration, so it's sort of this big science, and some of you have seen it. There's another one. This one's out at Stanford. That's actually about 10 years ago. And when the particles go into the detector, you reconstruct them by tracking, usually, you have to basically take advantage of the electric charge. So the electric charge going through a gas leaves ionization, which you drift to wires, and you pull signals off on the wires, and you can then in the computer reconstruct where the tracks went. Similarly, as they go into other parts of the detector, you basically have layers. You can have different types of things, but you might have crystals that give you a light signal when they go through that's proportional to how much energy they have. You might have layers of lead with liquid argon in between, so as the particles go in, they basically interact with the lead and turn into showers of other particles, and then as they pass through the layer of liquid argon, they leave ionization, which you can drift and get a signal. And then you have a granular detector, so you basically can get a picture of how much energy is deposited where for these particles, and you can end up sort of producing a map of the event. And from this, you can reconstruct what happened, or at least statistically try to do that. So it brings up lots of questions, such as how do the particles actually interact, and what forces interact in nature. And then, because we believe that the universe is expanding for reasons I'll talk about in a little while, if you extrapolate back in time, then things were much hotter and denser, and so all of a sudden you also need to ask questions like, how do these forces, which we may be seeing now, how do they change in energy or temperature? Because that's what's relevant if you want to talk about how the universe evolved in the early stages. So this is actually where you begin to marry the very large with the very small. So size really matters in this. In quantum mechanics, the uncertainty principle plays a big role in trying to understand the nature of forces. And so if you have something large, for example a car, and you want to know its position very precisely, you can bounce light off it. And you bounce light off it a couple of times, you can determine as precisely as you'd like its position or its velocity or momentum. But if you do this with a small particle, then the whole idea of the particulate nature of light and the fact that the particle, what you mean by a particle, becomes fuzzy when you're really looking at things that are very small. So what happens when you bounce light off a particle, this whole idea breaks down, because now you blast the particle. The particle will no longer be going the direction that it was going when you try to detect something. So that's sort of the essence of the uncertainty in quantum mechanics. And so Heisenberg quantified this, called it the Heisenberg uncertainty principle, basically saying we cannot have we cannot know both the position and the momentum of a particle to infinite precision. There's another form of this which is a little fuzzier to get across conceptually, but it also basically has to do with the wave nature of particles that we have in quantum mechanics. And that is, you cannot, if you have a very short-lived system, your knowledge of the energy is uncertain. And so the shorter lived the system, the more uncertain is the energy. And so if we combine this with Einstein's famous formula for rest mass of a particle equals mc squared, then we can begin to get a picture of conceptually how particle physics looks at particles. We don't think of particles as little BBs flying through things. We actually have to, if in quantum mechanics, you have to basically sum the particle. If you want to describe the particle, basically you're making a sum over all of the possible states in which that particle could be. And you can't just take a picture and know exactly what it was, because lots of fuzzy things can happen. For example, the particle can be bebopping along, and if it can just basically turn into other particles, effectively breaking conservation of energy, so long as they come back together in such a short time that it doesn't violate this principle. So over a very, very short time, I actually don't know very well what the energy of this system is. So that means that you have possibilities that are allowed over those very short time scales. So an electron, for example, can kick out a photon, which turns into an electron and a positron and comes back to the photon. And that's allowed in quantum mechanics. So if I want to understand the electron, I have to sum over all of these possibilities. Now, these aren't real particles because they can't be, because they can only exist for this extraordinarily short time. So it's a new world. I mean, it's completely wacky. It's very Harry Potter, right? I can make a Volvo appear right here. I just did. But it was over such a short time you couldn't see it, right? You've all had a friend like that, right? I had one who do that. He can nail two boards together. Yeah, it flies, it flies. Oh, it'll fly later. You have to pour water here. And I remember sitting here and sat there for an hour. I thought, you're a liar. It didn't go anywhere. But so this is sort of on paper in a sense, because basically you're using the fact that you can't know the energy very well if the time of the system is very, very short. And then what is allowed? You have to conserve overall momentum. You have to conserve overall charge. So there are rules to this chaos as to what it can split into. We call these particles virtual particles. So now, if you imagine that a particle is not like a BB, but it's rather instantaneously a cloud of these virtual particles, and exactly what they are, you have no idea at any time, then you get a fuzzy situation. So imagine we have two particles going close to one another, and they are each virtual clouds of virtual particles in a sense. What happens if this electron basically emits a photon that doesn't come back to this electron, but actually gets absorbed by the other electron? That photon may carry, the virtual particles do carry some of the charge and momentum of the original particle, if you want to think of it that way. If you exchange momentum, that's a force. So that is basically the quantum field theory concept of a force. It is the exchange of these so-called virtual particles. Okay? Or not okay. I mean,
when your head starts to feel like it's going to explode.
Yeah. I think this may be the worst part, but as long as we stay away from inflation. So, I mean, it does sound sort of ludicrous. I totally get that. It now enables us to actually talk about different types of forces. So let me see if I can. All right, so another way to think about this, it's really an exchange force, and that's not unfamiliar to us. If you have two people standing on ice and you have a big heavy ball and you exchange the ball, right? Then you'll exchange a force between them. So they'll move back and forth. So we do classically fully understand exchange forces, and this is really a fairly similar thing, except you're now using the loophole of the uncertainty principle to make it happen. So over the years, what's come out of particle physics is something we call the standard model of particle physics. So the atom itself is fairly large, about 10 to the minus 10 meters in size, and the nucleus is about 10 to the minus 14 meters in size, and then inside that nucleus we have evidence of protons and neutrons, and then if you use high enough energy particles, you can begin to see substructure in the protons and neutrons, and we call the particles that populate the protons and neutrons quarks. And insofar as we have yet been able to see, the electrons and the quarks are point-like. That may change as we go up higher in energy, because as you go higher in energy, the quantum wavelength of the particle you're using to probe becomes smaller, and you become sensitive to smaller distance scales. So it's the same reason that the electron microscope can see things that are smaller than the optical microscope. So we have yet to see structure to quarks and the electron, but
Can I ask you about the two sites you had on there? I understand the one is
with your
particle adventure.
Oh.
What's the second one about?
Oh, boy. There are lots of decent outreach sites in particle physics, and some years ago I was wanting to put links that were useful, and I went to this one and I can't remember what was on it.
Particle Adventure, the Particle Adventure has been like Fermilab, and it's wonderful for a
Yeah.
quest.
And actually, you may want to Google search it, because I'm pretty sure at one point I went looking for it, and its web link had changed somehow. And so,
Yeah, you just, if you Google Particle Adventure, you'll find it.
yeah. That's a very nice
Raptor
one.
site now too.
Yeah. And there's the University of Rochester created a worksheet for the kids to go through the particle adventure and learn everything they need and write down. So that's a good Common Core standard, that they're reading text and finding answers based on that text directly for those people at New York State.
Reading.
Yeah.
So, without getting into the history, but there is a lot of fun history. In the Standard Model of particle physics, we have 6 quarks and 6 so-called leptons. So the leptons, the familiar one is the electron, and then there's a fat electron called the muon, and an even fatter one called the tau. The muon and the tau are really identical in their properties to the electron, except for their mass. So because they're very massive, they'll decay basically into electrons very quickly. Then there are particles called neutrinos, which were a bit of a surprise. In beta decay, if you're basically looking at a neutron decaying to a proton and an electron, and people knew this, and if you go and you look at the electrons coming out of things that undergo beta decay, you find that that the electron comes out with a smear of energy. And if you just think about a neutron decaying into 2 particles, it shouldn't come out as a smear of energy. It should come out by momentum and energy conservation with a fixed energy all the time. But because it's a smear, Pauli hypothesized that there's another particle that's produced which we can't detect, that actually carries away some differing fraction of the energy depending on the particular event. And he called this, he actually called it the neutron first, but then the neutron was discovered, so they changed the name to the neutrino. And it turns out that we have different types of neutrinos, the electron neutrino, muon neutrino, and the tau neutrino. And these particles interact, they can go through a lot of matter. A couple of MeV neutrino, say, produced in the middle of nuclear reactions in the sun, can travel through something on the order of 53 light years of water on average before it interacts. So they go. Then we have other particles, the photon being a very familiar one, which nominally carry the force. These are the particles that get exchanged, the so-called virtual particles. So the photon, the gluon, and then the Z and the W.
Steve, can I ask you a question real quick?
Sure.
Because I know you did a lot of neutrino research.
Right.
Something the kids are crazy about is the new Einstein was wrong, the neutrino's faster than the speed of light experiment results.
They tightened the cables.
Everybody was excited about that except the physicists. It turns out that I work in a neutrino experiment in Japan that sends a beam from the east coast of Japan into the mountains of Japan. And we are one of 2 places in the world that could actually check that result. And I was at a collaboration meeting the week that thing was announced. I was in Japan. And so we did talk about it, but I don't think I ran into a single person that
was excited?
Well, I mean, we were all excited because it's sort of fun, but nobody thought, it's a really complex experiment.
Yeah.
Everybody looked at the paper, watched the seminar, and knew that the opera collaboration at CERN had done a careful job trying to do all the right things. And
Do you want me to turn the
it's just
camera off?
complicated.
Do you want me to turn the camera off?
I'm not going to say anything I get to.
Okay.
No, actually, I'll stand by that. As far as I know, they did a very careful job, and nobody knew exactly what was wrong.
Yeah.
It does appear about a month ago or 3 weeks ago, they released news that they found 2 things in their that were quite right. So one was a loose optical connector on the back of the GPS, and it appeared when that news came out that might actually adjust their timing to the point where this effect will go away. Now, as far as I know, they haven't repeated the measurement yet with the Titan connector. And there are experiments at Fermilab and in Japan that will be duplicating. But I think all scientific revolutions start by being absolutely unbelievable, and this would have been very much unbelievable. I mean, basically would have said relativity, either relativity is wrong, or it could be evidence of multiple dimensions, that basically you have some particles constrained to be in the 3 dimensions we know and love, and others that can actually go outside of that. So if when you have sort of the curved space of general relativity or whatever, you could have some particles that could cut across, and I mean that might have been one idea. So if it holds up, it will truly be a huge revolution. But I am still teaching relativity in my classes and have no intention to stop. Did I say enough?
Oh yeah. I just Vern, I'm just not in the loop when they have this groundbreaking news. They never have the follow up if they find that the news wasn't true.
Isn't that interesting? I've noticed that. I've noticed that.
That's what social media is for.
Yeah.
So we'll see if the Higgs goes over too.
Yeah.
It might be a bad year for CERN. I don't know. The issue that I have was not with the collaboration. The issue I have was really with CERN management, putting it out there. I mean, once you've got it out there, I really can't blame the press for making a big deal out about it. And no publicity is bad publicity. So
Yeah.
I actually think anything that gets people excited about science is a good thing. So I'm not even too harsh on CERN management about that. But it is sort of sad, because what does get lost in this very often is really the whole process of science. The fact that these people did a good job, and it is all about good science. They come up with something, it's patently crazy, people have to check it, they keep looking, we figure out what they did wrong, we make a more precise measurement, and we move on. Or they did it right, and we have a total revolution. I mean, that's how science works, and that to me is the very exciting part of this. But because the follow-up gets lost because nobody's interested in it, in a sense, that whole thing gets lost. But it's a good story that we can all tell. So of these particles, we also have antiparticles. Basically the same as the particles, except they have opposite electric charges. And there are reasons why it's good that we have antiparticles I'll talk about in a moment. So I mentioned, so this exchange of virtual particles is what gives us the forces of nature. And it turns out we have evidence of 4 different forces in nature. And it's actually the type of particle that gets exchanged gives us the indication of the force. So for example, photons are massless. So if we have 2 charged particles exchanging a photon, a virtual photon, because photons are massless, it means that I can create a photon that has basically negligible energy. So I can create a photon in this virtual cloud and violate conservation of energy by as little as I want, which means it can exist for a very long time, because the uncertainty principle just says that the more certain I am of the energy, the longer over the time that this thing can exist. So if the photon can exist for a very long time, at the speed of light, it can go very, very far. And so this is why the electromagnetic force has an infinite range, basically, in this picture. On the other hand, in the weak interaction, where the particle that gets exchanged is either called a W or a Z, these particles have masses that are roughly the same as a gold atom. They're 80 GeV, so it's 80 protons worth of mass. And this is a fundamental particle. So to create a W or a Z, I have to violate, if you wish, conservation of energy by a massive amount, which means the W or Z as a virtual particle can only exist for an extraordinarily short time. Even at the speed of light, it can only go a very, very short distance. So what that means is that for two particles to exchange a W or a Z, they have to come really close to one another. And now it's just a game of darts. You can throw a lot of darts and never hit the bullseye itself, because the phase space of hitting the bullseye is vanishingly small. So what that means is that it is very seldom that two particles will exchange a Z or a W. So what we call the weak interaction isn't actually weak when it happens. It just almost never happens. And this neutrinos, by virtue of the fact that they have no electric charge, and they also don't interact via the strong force, which I'll talk about, they only interact via the weak interaction. That's why a neutrino can go through 80 light years of lead or whatever without interacting with anything, because you just never. So in order to see neutrinos, you have to have lots of neutrinos or a big detector and stuff like that. So that's sort of a way in which you can begin to talk about the differences in these types of forces. For the strong interaction between, that basically is what binds quarks and the protons and neutrons, the particle that is exchanged, which we call the gluon, actually carries the charge itself. In this case, we call it a color charge. And that actually changes qualitatively the whole fundamental nature of the force. In the weak and the strong interaction, basically as I move the particles, as the particles approach each other with less distance, the force in a sense becomes weaker. And in the strong force, if I take two particles that are exhibiting it and I try to move them apart, the force between them becomes stronger. So it's a very different force. And I'm going to let that one lie unless you want to talk about it later. I can lose a lot of time with it. So we think we have these four different forces of nature that come from exchanging these different types of particles that have different types of charge. And this basically is what we call, this is the input to the standard model of particle physics. It does open up some fun things, because with this uncertainty principle, the whole concept of the vacuum is completely gone, right? All of a sudden, because of the uncertainty in energy, I could have nothing. And truthfully, if I take a small region of that nothing and I ask, what do I know about the energy in that nothing? If I look at it over a short enough time, I don't know much about the energy there. In fact, I might have an energy fluctuation. This is what we mean when we say quantum fluctuation. There could be that I have a lot of energy in that spot over a really short time, and if I have a lot of energy sitting there, it will basically pair produce into a particle and an antiparticle, which is why we need antimatter, because we need to conserve charge when we do it, so we can create a positron and an electron out of nothing. And that's fine, so long as it goes back into nothing over an extremely short time. So as you look at the vacuum over shorter and shorter time scales, it is actually a seething mess of particle and antiparticle pairs. So physicists will talk about the quantum vacuum, and it's a complicated thing. So if you're a particle moving through the vacuum, you can actually interact with the vacuum because you can interact with these particles in a sense. And so this is more or less how you can explain mass, because mass is inertia. So in the standard model, these particles are interacting with something in the vacuum known as the Higgs, which I'll talk about in a moment. But it turns out that for strongly interacting particles, they will actually interact with quark-antiquark pairs that are in the vacuum, and it actually can add mass to particles. So the vacuum is very complex. You don't actually see quarks because when you pull them apart, the force between them becomes greater. You get so much energy involved, they'll actually pull out particle and antiparticle pairs instead. And so you'll get other particles. And the kinds of particles we typically see are 3-quark bound states or quark-antiquark bound states. And if you have a 3-quark bound state, we call them baryons. There are lots of stupid names in this business. Actually, historically, they're very interested, but we have up, down, charm, strange, and top and bottom quarks. And there's actually good reason for those crazy names, and we can talk about it if you want, but I'll go late if I start doing that. Baryons, that's Greek for heavy, and mesons is Greek for middleweight, because the first baryon really was the proton, which is a heavy particle, and the mesons that we're seeing are sort of less massive than that, but heavier than electrons, so things like pions and kaons. Typically, we just see the electron and protons and neutrons, which are baryons. So in the world, we have all these fundamental particles up top, but what we normally see are just the bound states, the baryons, the two up down and down quarks, or two downs and an up quark. And those particles, the protons and neutrons, go into nuclei, and then the electron is held into the atom by the electromagnetic force, Coulomb force. And everything else you don't normally run into because we don't have enough energy to create these other particles typically, and they'll decay into the lightest states. But as you start thinking about cosmology and you go up in energy, then all of these things become very important. There's one last piece in the Standard Model that I'll give you a very hand-waving sort of, I want to mention because I think it's fairly interesting. It's also in the news a lot. What do we really mean when we talk about the Standard Model? There's an important piece of it, which is called electroweak unification. It turns out that we had evidence of these 4 forces, but they seemed like 4 distinct forces. And the electric force, the electromagnetic force, the weak force, and the strong force could sort of be understood in terms of this quantum field theory picture at some basic level. Gravity didn't quite fit in, and still doesn't for this particular way of looking at things. The problem was, if you started to look at the details, if you take quantum electrodynamics, which is this picture of the exchange of the photon being the force between 2 charged particles of Feynman fame, right? It was developed in the 30s and 40s and works very well. If you look at the symmetry in the equations, it turns out that you can't have mass terms, which means QED is a great theory, but it doesn't work between particles that have mass. The whole theory doesn't actually hold up, even though you can use it and you can calculate things to Gnat's eyebrow or whatever, because electrons are pretty light. But fundamentally, it actually has a real problem. You can't have massive particles in it. The same thing was true for the weak interaction. People had theories of beta decay and such from the 1930s. And the theory could describe a lot of the things we would see, but fundamentally, if you looked at it, it wouldn't work for massive particles. So it turned out that we have these sort of great different theories, but you couldn't have massive particles in them, so it really couldn't describe nature. So a whole group of physicists worked on this. In the end, Salam, Glashow, and Weinberg came up with something which we call the Standard Model, or the electroweak model, where they realized that theoretically they could take QED, the electromagnetism, and the theory of the weak interaction, and basically add, ad hoc, a new particle, which we call the Higgs. And then they could play a little bit theoretically, and lo and behold, sort of mixing and matching terms and making some choices mathematically, out pops a theory that described the weak interaction, the electromagnetic interaction, and allowed mass terms for the particles. And that's what we call the electroweak interaction. Okay, and these guys were given the Nobel Prize for it. This particle that you have to add in to make this whole thing work is called the Higgs, after some guy named Peter Higgs. This theoretical way of this mechanism that they used mathematically in order to unify these theories was actually invented prior to their work. And it's called, we call it now the Higgs mechanism, but it was actually invented by about 6 folks, one of which was Higgs. But I did want to mention, one of them was also Carl Hagen, who's at the University of Rochester. Okay? So if in fact the Higgs is ever actually discovered, there is a problem, because there are really 6 people that could get the Nobel Prize for having invented the whole concept. And they don't give it to 6 people, so then it becomes a popularity contest. And so,
Or you wait until some of them die.
or you wait until some of them die. That could be, yeah.
Solves the problem.
So the scale apart, yeah, that could be it. At any rate, so that's the thing about the Higgs is electroweak interaction, the standard model. We've been doing lots and lots of experiments and testing it to gnat's eyebrow, and it works perfectly insofar as we can tell. There really is no solid evidence of something that breaks the standard model, with, except for the exceptions that I probably won't mention. I mean, we have discovered neutrinos have mass, which isn't really in the standard model, but it doesn't really change this whole idea of the mechanism. Because the standard model works so well, what we know is that something does what the Higgs does in that model. We don't know that it's actually a fundamental particle that's called the Higgs that we're looking for. What we know is that something does it. So it could be that life is more complicated, and there are, say, particles at much higher mass that, for some reason or another, at low energies, they look, one of them will look like a fundamental particle. And so as we go up in high energies, we may find that that isn't so fundamental. In the standard model, you're assuming that you have this fundamental particle that's sitting there, and that's what does this. So people are very excited about looking for the Higgs, because it might actually be a big step into something totally new and different, because we don't actually, and the truth is, if we just have a fundamental Higgs, then there are lots of questions that we do not have answered. Okay, the masses, the Higgs allows us to have mass, but it doesn't actually tell us what the mass scales are, and the particles vary dramatically. Top quarks weigh 170 GeV. That's 170 protons. W's and Z's, weigh 90 protons. The electron is a half an MeV. I mean, what sets the scale? Why are these so crazy? Most scientists like to think that there's a good reason, but we don't know it yet. So there are many other questions. There are lots of very fundamental questions in the standard model. But it's actually, in and of itself, we know it can't be the last answer. So probably there isn't such a thing as just a fundamental Higgs, but people talk about it. So this idea that CERN is on the threshold of discovering the Higgs, it's sometimes sort of a model-dependent statement. They are, if in fact they discovered just a standard model Higgs, it would be truly a big puzzle. But okay, so that's why people are very excited about it. I forgot. I didn't notice when I started, but just let me know if I start to go too long. So.
You're fine with me.
Okay. So I wanted to talk a bit about the very big, and then we'll talk a little bit about how these things fit together. So telescopes are time machines, basically, because the light that's coming into your telescope was emitted by whatever object it was very long ago because of the finite speed of light. So the further out we look, the further back in time we look, and light moves pretty fast. It actually goes from New York to San Francisco. I think it's like a 60th of a second. I wrote a little book called Relativity in Quantum Physics for Beginners. And it's basically a graphical book. And God, it's horrible. In spite of editing this thing, and again and again, myself, the editor and everything, the only evidence I have that anyone's read the book was when I started getting emails about the errors that are in the book. So, one of them was somebody checked me on this, and I guess I had rounded when I made this thing up. I think light actually goes 60 times between New York City and San Francisco in a second. But anyway, it's still fast. So if you look, it was discovered as people began to realize that there were these fuzzy things out there. They started, Vesto Slipher discovered that when he looked at galaxies, most of them that he could identify were actually moving away from us. And he could do this by looking at the Doppler shift. Now in this crowd, you guys all know what the Doppler shift is, so so the point of this demo isn't so much to explain the Doppler shift, but to show you this cool demo. I think it's a lot of fun. So you can vary the speed of the particle, and then you've got the wave fronts that are emitted by the particle, so you can see that the wave fronts are closer if you're looking at it from the direction it's approaching, and further apart if you're looking at it from the direction that it's moving away from. So this whole idea of the optical Doppler effect is that the object's moving toward us, the light is bluer than, and if it's moving away from us, it's shifted to the red. So he used this effect, and he found that most of the galaxies were actually blue shifted in the nearby area. Then Edwin Hubble and Milton Humason. Now Humason, as I understand it, was actually a janitor at Mount Wilson who started looking over people's shoulders, and was a very smart guy, and before long became a core member of the staff. And Hubble and Humason took measurements of distance that Hubble had figured out by looking at the Cepheid variable stars. They're stars where they oscillate in brightness, and the period of that oscillation is, from the period of oscillation, you can actually know the absolute brightness. And if you know the absolute brightness, you can get the absolute distance. And so Hubble was looking at that, and the two of them actually correlated the velocity with the distance. And you know, you look at this and you go, well, they're sort of proportional to one another, and it's pretty amazing that out of this they inferred Hubble's law, which is that the further away something is, the faster it is moving away from us. Modern data looks more like this, and it's over a much larger distance. And out of this actually comes the expanding universe. And it's interesting, to me, it's not completely obvious that this data says that, so I had to think a little bit about why that is. And my favorite analogy is actually one, oops, where did I have it? I must have killed that slide. So my favorite analogy is actually one of raisin bread. If you take dough, raisin bread dough, okay, and the raisins are so close to one another in the dough, and you allow it to rise, then raisins that are close to one another during the rising will move a little bit apart. Raisins that are far away from one another in the dough will move apart quite a bit. So if you calculate the velocity of the raisins moving away from one another, you'll find that raisins close to one another over that same amount of time move apart just a little, so the velocity is small, and the ones that are on the far part move much, much more. And the reason is because the bread dough is expanding throughout. And so in a model where the actual space itself is expanding, things that are far away from us will move away from us much, much faster. So out of this data comes the unavoidable conclusion that the universe is expanding, and we can actually extrapolate back in time to a point, and the current date is about 13.7 billion years if you look back in time. So this is sort of the origin of the Big Bang model. And so, in fact, I'm going to describe for you the hot Big Bang theory. And there are a number of players. There's Einstein. This is Einstein's field equations that basically describe the geometry of space-time under the effect of gravity. And Alfred. So these are a few of the players. And it's a little more complicated than this because the Big Bang theory in and of itself is obviously wrong. But it's also obviously right. So I'm going to describe to you why it is right. And later, if you want and we have time, I can tell you why it's wrong and how it's fixed. But for interest of time, I sort of threw the latter part out, but maybe that's the most interesting part to some of you, so I don't know. At any rate, the idea in the Big Bang is you extrapolate back in time, and just as if when you take a bicycle pump and you compress the air, you get a hot nozzle. If you adiabatically take a universe and you make it smaller, it will be much hotter and denser, okay? And the thing is that, and we all know that if we take atoms and we put them in an oven and heat it up to a few thousand degrees, you'll ionize the atoms. So in fact, what we see in the universe depends very much on the average interaction. And as you go up where the average interaction between particles has an energy that is large compared to the mass of the particle, you can create other particles quite freely. So the idea that we nowadays have protons and neutrons and electrons is partly because we live in a world where the average interaction is very low. But as things get very hot, the world can be quite different. So in fact, the idea is that in the early stages, we had basically a primordial soup of very hot, dense particles. Things were so massive, so energetic, that all of the very massive particles you can imagine might have existed. And in fact, particles that we understand and physics we understand can take us all the way back to some pretty short time, like 10 to the minus 40-ish seconds after the Big Bang. No, that's too much. 10 to the minus 25, 28. Once you start to get to about 10 to the minus 30 seconds after the Big Bang, physics as we know it starts to become fuzzier and fuzzier. We know less of what's going on. But we do have real theories and that people are arguing about at about the 10 to the minus 40 to 10 to the minus 35 seconds after the Big Bang. Okay? And we are actually producing in the accelerator environments that would have been common, interactions that would have been common at about 10 to the minus 25 seconds after the Big Bang. So that's starting to get physics that we understand at the large accelerators. At any rate, let me fast forward a bit to about 1 microsecond after the Big Bang. At a high enough energy, the force that binds quarks and protons and neutrons actually is very weak. And so that means that quarks were sort of freely moving, so we call it a quark-gluon plasma. At about 1 microsecond, the universe is expanded and cooled enough that those quarks will actually condense into protons and neutrons. So that's a phase transition we call the quark-gluon plasma into well, it's quark-gluon plasma before, and then turns protons and neutrons at about 1 microsecond. Then, in the first 3 minutes, we get the formation of some light nuclei. And there's some funny things happen. Once you form a neutron, it has a lifetime of something like 20 minutes. So we have a universe that's full of protons and neutrons are starting to disappear. Okay, they're decaying away. And at the same time, the universe is expanding. So we have the strong force where protons and neutrons are starting to stick together. Things are cooling off so they don't get knocked apart so easily. And the neutrons are decaying. So it turns out that there is this time window where things are dense enough that they are hitting each other and you're adding neutrons in and forming light nuclei. And that, of course, happens less as the universe expands, and the neutrons are decaying away. So there's this narrow window where you can actually form light nuclei. It's all over about 3 minutes after the Big Bang. Okay, and you can take a model of a pot of hot protons and neutrons and follow this thing through these processes. This is all something you can model and actually come out with hardcore predictions of what fraction of light nuclei do you expect to see. And this is known as Big Bang nucleosynthesis. I'll say more about that in a moment. It takes another 400,000 years before the temperature of the universe drops to the point that electrons will begin to glom onto the protons or the light nuclei and you get neutral atoms. This turns out to be an incredibly important period because if I take the charged particles, the protons and light nuclei and electrons, and they're a plasma, that is, they're not neutral atoms, if I shoot a light beam there, it's like shooting a light beam into fog. The light scatters and it's opaque. And so we say that the interaction length for a photon is very short. At 400,000 years, when the universe cooled just enough that neutral atoms began to form, the universe became transparent. So whatever light was bouncing around at that time has traveled since then. Okay? And that light is what we call the cosmic microwave background. So when we look at the cosmic microwave background, it's microwaves because it was about 3,000 degrees. It was very hot and UV at the time it was bouncing around. But now the universe basically is expanded. And with that, the wavelength of the light, one way to think about it is the wavelength of the light is expanded to the point that it's microwaves now. So the entire universe is glowing in microwaves, and the light that we see everywhere we look is basically light that was bouncing around in the universe at 400,000 years after the Big Bang. So people are intensely interested in studying this because whatever you see at that time is sort of a picture of the universe at 400,000 years. And we are a product of that. So the idea is that non-uniformities in this microwave, in the universe at this time, were places where you began to get condensation and where you get gases to collapse. Things get hot, you start fusion reactions, and you start stars, and then the stars go through their lifetime and go supernova, and in the process they create heavier elements, because in the fusion processes in the stars you can only form elements up to about iron. And anyway, so things then go, and then you get to today where lots of important things happen. Okay, so accelerators are really time machines as well. So as we go up in energy, we're literally looking at processes that are back in time. And so this is what I mean when I talk about the marriage between the very small and the very large in part. So for us to understand each of these phase transitions, we can use accelerators to go and look at the physics of the interactions between the particles that we think were around at that time.
Might be a race
Yeah,
of fate.
I got it. This is the slide. I put it in the wrong place for the talk.
I ate one.
You know, people think about the Big Bang as this explosion of something into nothing, but that's not it, right? The universe, the space itself, is what's expanding. Okay, and it's a weird concept, but so I tell my students more like a butt growing than a zip. It grows from within, right? Or a gut. So why do we believe in this wacky idea? One is because we have the expanding universe, and that data tells us that this picture sort of may be the case. So you could try to imagine an idea where space can expand, but you can't go back to a point, but it's pretty concocted. Although, you know, the universe coming out of a point seems pretty concocted too, so what evidence can you find? Well, I mentioned that there's a very core prediction in this theory that you should have this light from 400,000 years after the Big Bang that's just bouncing around all over the place. It should be microwaves. And it turns out in 1964, these guys were wanting to take a microwave antenna and change it from communicating with satellites to doing radio astronomy, and they had this noise they couldn't get rid of, and they cleaned the bird crap out of it, and they still couldn't get rid of this noise, and they had a real puzzle on their hands. Everywhere they looked, they seemed to have this microwave noise that followed a perfect black body curve, meaning that it looked like it was coming from an object that basically was just glowing, right? Which is what the universe was, so you expect it to be black body. And there were some guys at Princeton at the time who were working on this idea of the Big Bang, trying to understand what should come out of it. And these two groups mutually knew somebody who happened to know about each of them and got them in contact. And lo and behold, the guys at Princeton came and realized that these guys, Penzias and Wilson, were seeing the Big Bang, basically, the evidence for the Big Bang. Sort of unfair for the group at Princeton. They were in the midst of building a detector to actually look for this, okay? These guys got the Nobel Prize, so it's sort of one of those awful, sad stories in science. Sort of sad, sort of not. It's still pretty exciting. So the discovery of the cosmic microwave background is a huge reason to believe in the Big Bang. There is another. I mentioned the idea of taking this pot of protons and neutrons at a high temperature and basically allowing it to expand and cool. And then you can predict exactly the ratios or the fraction of light elements that you expect to see. And boy, this doesn't look very good, but as you look as a function of time at about 3 minutes is about here. This is time into the, I'm sorry, this is temperature, which effectively is, this is time. So this is at about 3 minutes. And you start out with just protons and neutrons, and as time evolves and things cool down, they'll begin to glom onto one another, and you begin to get some light elements like hydrogen and helium and tritium and beryllium, etc. But you'll note that at about 3 minutes, because the free neutrons have all disappeared at that point, you've pretty much set how many of these you have, what the fraction is. And then some of them will decay away. So the neutrons are decaying away. And that means, and then these now become basically flat. And so we know what the ratios of light elements should be in intergalactic space as a function of time if you believe in the Big Bang model. And people go and look, and the data supports this. So this Big Bang nucleosynthesis is, again, an independent and big reason to believe in the Big Bang.
So you got lithium, I mean, is that the biggest?
Lithium, they're probably, if you look at the papers, you may see small amounts of other things, but this is a log scale, so you're starting to get down to pretty small numbers here. So if you can look at the cosmic microwave background with high enough resolution, then in fact you can see that it is not all at one temperature. It actually looks like it was emitted by black bodies at slightly different temperatures. So in general, in the Big Bang theory, you should have complete uniformity in this thing as it's expanding. There's nothing to break its uniformity in the Big Bang theory in and of itself. So on the other hand, we live in a non-uniform world with dogs and kids and planets and stars, so we know that something had to break the non-uniformity. The big argument is exactly what and how that happened. But when people learned to look at the cosmic microwave background with a high enough resolution, they found that the temperature varies by about 1 part in 10 to the 5th as you look across. And this is literally a picture of the full sky in microwaves where the color coding, the differences in the colors are at about the level of 1 part in 10 to the 5th. So it takes a very high precision instrument to do this. Now, this basically is telling you in these different parts of the universe, you had regions that had slightly hotter or cooler than others. And this means you're going to get non-uniformity in the amount of mass that is produced when it cools off enough that you can actually, there's a correspondence between the amount of the temperature and the amount of mass in these regions of the universe. So you get so the clumpiness is clearly there at 400,000 years after the Big Bang, and you can. There's a nice video people have created to sort of show you how these different temperature regions condense into, sort of are coming from different amounts of gas, which condense into different densities of stars, and you get the clumpiness. So people have been studying the large-scale structure of the universe, basically mapping as a function of depth in the universe, the basic structure, density of galaxies and things like that, and trying to make it correspond to basically the density of the dots that you see on the cosmic microwave background. Okay, you can learn some pretty cool things out of this, actually. In Einstein's general theory of relativity, you interpret gravity as a curvature in space-time, but you could have any curvature. So one of the questions is, what is the curvature of space in our universe overall? And by looking at the sizes of the dots on the cosmic microwave background, the sizes of the structure, you can actually get a measure of the geometry of the universe. That is, if the universe is flat, from the theory of the Big Bang, you have a sense, there are limits as to what the sizes of these structures can be, partly due to causality and what's creating them. Because basically you're talking about density waves in the early universe, because you have matter there, and basically you're talking about non-uniformities in the density, so it's just like waves. And in fact, people will often call this there are analogies between the structure and literally wave theory or sound theory. At any rate, you can get a sense from first principles what the size of these structure ought to be, and then you can go and look, and if the geometry of the universe is flat, if basically from one end of one dot to the other end of one dot, the light comes straight at you, you'll see a certain size. If it comes like this, it will look bigger. If it comes like that, it will look smaller. So if when we look at the geometry of the universe, we look at the sizes of these structures, we basically can get a measure of the way the universe is. Now, one of the things that has come out of this in the last 10 years is that the space in the universe is flat. And in general relativity, that is a completely weird and special case because there's nothing that constrains it. So you have an infinite number of curvatures and we're flat. So therefore, there has to be something in the cosmology that drives us to be flat. This is one of the big fundamental problems with just the Big Bang Theory in and of itself because it has no mechanism to drive space to be flat, and yet we've measured it to be flat in the last few years. Now,
Quick question, sorry.
yeah.
The two videos that you just showed, the two short videos, are those available out there?
Yes.
They're trying to
Yes. So
teach
the
this
thing to
in
do is
classes.
Google WMAP.
Just
Yeah, and there's some, in fact, I'm certain on earlier versions of this talk,
Okay.
I have links. I mean, I gave credit as I ought to be giving credit for all of these. But,
Okay.
you know, it's sort of funny. You give the talk so many times, you start pulling these things over, and then you just, one time you do it, you forget to bring the credit. You can tell I made this slide up yesterday because I have the credits on here. So, whatever. Happily, surprises happen in science, always, which is one of the great things. And in the last, well, it's been a while. We've had indications of this one for quite some time, but I think there's become something of a consensus in the physics community about this. If you look, it's been sort of a quiet developing story for many years. So historically, it's now sort of a slam dunk when you look at it, but much of the history really is coming from 1970s or so, where people did measurements of, and I should have put the people here, but anyway, if you do measurements of the rotation rates of stars as they go around the galaxy, we know about stars and we know about gas clouds and galaxies and everything. So if for a given amount of light production in a galaxy, we have an idea of how much mass is there. So astronomers have been doing this kind of stuff for a long time. So that means we know how much mass there is as a function of radius that's at least associated with the luminous matter that we see. And for near enough galaxies and a powerful enough telescope, you can resolve the stars, and you can actually look at the rotation rates of the stars as a function of distance. And under Newtonian/general relativity physics, there's a particular form that you expect to see. And in fact, what we find is that it doesn't fit that at all as you go out. And the only way to make the data fit, well, there are two ways. The way to make the data fit what we see is either gravity takes on a completely different form as you go to very large distances, which appears not to be the case as far as we know. Or there's a lot of mass, in fact, about a factor of 8 to 10 times more mass than we see, which is present generally in a form that is not so much in a disk form for galaxies, but it's more of an ellipsoidal form, that we can't see. We can't see it because it must not interact with light, which means it has no electric charge. So we know it's neutral. And we call this dark matter because we're so ingenious when it comes to names, right? And this, we don't know exactly the form of the dark matter, but 20 years ago, people were talking a lot about it could be fundamental particles, it could be that it's matter locked into dark stars, stars that weren't formed, machos and things. So people people have done lots of measurements to try to quantify. And so it is true, there is matter in objects that we don't see that are conventional objects, like dark stars. There is mass, it turns out, in neutrinos, and there are lots of neutrinos in the universe, but that's not enough to account for this. So we actually believe there's a significant chunk of mass in the universe which we are unaware of, which we've yet to really figure out what it is, and it's called dark matter generically. Another thing that was noticed, people tried to do basically the Hubble measurement on steroids. So they get a telescope and they look at supernovas in different galaxies far, far away. You look at supernovas because they're very bright, and it turns out for certain types of supernovas, the way in which the light curve turns on and off allows you to know what the absolute luminosity of the supernova is. So if you look at enough supernovas, you can basically get a measurement of distance to lots of different stars, and you can use the redshift again to figure out how, what the speed is. So you basically can plot velocity as a function of distance and measure Hubble's constant as a function of time in the universe. And so these people did this. There were a couple of collaborations that did this, and these guys, Perlmutter, Schmidt, and Rees, are basically credited with pushing this. Instead of discovering that it's a straight line all the way out, they actually discovered it has curvature. In other words, the expansion rate of the universe, you might naively expect to be slowing down because gravity is pulling you back. What they found is it's actually speeding up. So you can put that in Einstein's field equations. You can basically write down your equation that describes expanding space. And in order to have it accelerate, you have to add a term which has units of energy. And we call it dark energy. So what do we really know? We know that in our understanding of the universe, there is a term that corresponds to energy that allows the universe's expansion to accelerate, and we call it dark energy. And welcome to the world of experts on dark energy. I've now told you about all we know. There are lots of ideas, okay, but people are basically trying to figure out what this is that we're really talking about. And just to point out, I mean, now we have sort of this new thing, this dark matter, which is clearly more gravity than we thought was there, and we have dark energy sort of pushing you out. So there's a lot of new stuff that's really, in a sense, only 10 years old, and the dark matter has been around a while longer. So we can combine all this and actually learn some pretty interesting things by looking at the cosmic microwave background. And the way to think about this is we can look at the size of the different structures in the cosmic microwave background. And a way to think about that is if I have a lot of energy or a dense region in the early universe, for example, of course there's going to be more pressure there, so it's going to expand, right? How much pressure you have depends on how the particles interact with one another. If a lot of the energy is dark matter, the dark matter doesn't interact very easily, right? I mean, we don't, in a sense, the structure freezes out much earlier. So if I change the amount of dark matter in the world, in the universe, I will actually change the sizes of these different density regions, and that literally changes the sizes of the hot spots you would see on the cosmic microwave background. Similarly, if I have a lot of dark energy, I'm expanding much, much faster, which will also change the size of the dots that you see in the cosmic microwave background. So if I go and I make a careful study of the sizes of the structures on the cosmic microwave background, I'm actually sensitive to how much dark matter there is in the universe and how much dark energy and stuff there happens to be. So people do this, and the way they do it is they make what's called a power spectrum. So basically, this axis is a measure of the size of dots, and this size is sort of a measure. This axis is sort of a measure of the frequency with which you see things at that size. So you see a big peak where you see most of dots of roughly that size. And just to get a sense what this L effective is, this would be if you lived in a universe of L equal 2. This would be if you lived in a universe of L equals 16. So you can see that as you go up in L, you're looking at smaller and smaller structure. So in fact, if you go and you make measurements of it, you get this data from lots of different experiments, okay? And you do actually see structure here. And if I now go and I make a model of the universe, I will have a prediction for exactly what this structure should look like. And so the hot Big Bang model with something called inflation actually fits the data very, very well. But in order to make it fit, I have to have certain proportions of dark matter and dark energy. And so we now have this thought that everything that you and I know and are used to and spend all our time talking about constitutes about a quarter of the universe. And then, I'm sorry, not a quarter, a very small fraction. Then we have a lot of what we think of as matter, but it's dark matter, so we're not quite sure what it is. But it does interact gravitationally, that much we know. And that constitutes about almost a quarter of the universe. Combined, this is about 4% of the universe. Everything we know is like 4% of the universe. And then if you look at this if this is an energy budget of the universe, most of it is actually tied up in whatever dark energy is, which we don't actually know. So the more we know, the less we know. And this is really what people are doing. Okay, so great progress, lots we don't know, lots of questions, nature of dark matter, nature of dark energy, what does what the Higgs does, and you know, on. There are lots of fundamental questions that people are working on. So the LHC, you know, I can talk about steps that people are taking. The LHC is one of them. Maybe I've already talked enough. I'm happy to go on. I'm happy to talk about other things. I'm happy to break up into groups and people need to do other stuff. But I did want to point out a little bit of self-promotion, but I actually think it's a useful thing. I did write a book that was published about a year ago called Visions of the Multiverse. And really, at Rochester, we had a course which was called Physics of the Natural World, which when I taught it, I tried to basically tell the story that I've been telling you, sort of this marriage of the small and the new and all this exciting stuff. And I thought it was pretty cool, but you know, what student's going to sign up for physics of the natural world? So I thought, okay, what I'll do is talk about different types of multiple universes, because there are lots of weird concepts out there. But in order to do that, I have to talk about all this other stuff to give them background. And so this book actually gives all this background and then has a multiple universe theme that ties it together. So it's a survey of a bunch of different multiple universe concepts. And, but in the process, it's really also telling the story about the evolution of particle physics and the uncertainty principle and cosmology and you know, the chapter on string theory and how these various things tie together. So it's sort of a fun book. I wrote it in part because when I pick up Brian Greene's books or most of the popular books, I have to work. I mean, I'm not sure who they're written for, some of them. I mean, Brian writes really great, but sometimes I pick them up and think, who's reading this? A lot of people are, but to me, they're not so accessible. So the intent of this book was to make things more accessible than they typically are. So you might find it fun. You may find that you have a student that might benefit from it. I mean, pick it up and take a look at it, see what you think. But it's designed to hit many of these topics sort of as in a more accessible way than it's typically done. So.
Take questions, you know,
Yeah.
people got questions.
I just have a comment. When I thought going way back to the beginning of your slide, you talked about the Rutherford model. I always like to, when I'm teaching modern physics, say, okay, let's take all of us in here. We're the mass of the nucleus. About a 1 kilogram block is the mass of the electron. And now all of us have to go in, if this is a 10-meter room, we have to go into something a little bit smaller than a millimeter. Because I think part of it is the size scale, but it's the density scale.
Yeah, yeah.
That
Yeah, I think it's always, I think the fact that atoms are almost all empty space is often lost, and you know, because you know, you always draw the nucleus too big. That's true. Yeah, I think at some point, I calculated I took the density of the nuclear matter, and I calculated what would be the conventional gravitational mass of a golf ball sized piece of nuclear matter. And I forget the number now, but it's something on the order of 70,000 fully loaded Nimitz aircraft carriers. I mean, it was on that order. It's some absolutely outrageous thing. So I use that sometimes.
So are you teaching that course now?
Yeah, I call it Visions of the Multiverse, and the initial intent that I used was to try to draw students in to talk about all this fun stuff. And actually, it's sort of funny. The first time I taught it, we had failed to list it properly in the group of, because it's really for non-majors, and so there's a requirement. They have to, if you're a humanities major, for example, you have to take a cluster of 3 classes in the sciences. And so this is aimed at those students. But there's a certain place they go to find the proper classes, and they call it the cluster search engine, and we failed to list it there. So then the second time I taught it, it was listed with the incorrect title and the incorrect course description. And I actually had to go into class and say, well, welcome to a classic bait and switch. You signed up for this, and I'm teaching that. And you know, it was pretty. So I have yet to actually try the marketing ploy for this class. So hopefully before long we'll try that.
I don't speak for the other computer program.
You got time? I mean, I got slides. I'm moving.
No, we have time. I mean,
Okay.
I know Dan was going to show us the railgun he put together.
I need to present, and I certainly wouldn't recommend.
Yeah, okay.
Physics class anymore.
All right. But yeah, I mean, basically, I have a couple styrofoam cups that nobody really needs to see, but that's
All right, well,
I just got some filler there.
I got
yeah.
some slides, but we can probably do this in 5 minutes.
Why don't you still?
Yeah.
So the problem is, when you take the Big Bang seriously, it just can't be right in and of itself. And one reason is that flat space is a very special case in general relativity, which seems to describe large-scale geometry, things like large-scale gravitational things very well. But something has to cause the universe to be flat. And in the Big Bang, you could basically have any arbitrary geometry depending on how much energy and mass you have in it. Then there are other problems. One is in the Big Bang in and of itself, you extrapolate back in time, you're extrapolating back to a point. And physics as we know it just goes crazy when you bring things down to a point. Then there are actually problems that are even worse than that, okay? One is called the horizon problem. And I have some good slides on this, but I don't have them in this talk, sorry. And I'm not going to go digging, but basically let me give you the idea. If we look this direction in the cosmic microwave background, and we look that direction in the cosmic microwave background, we see the same color to 1 part in 10 to the 5th. Basically, that means the universe at 400,000 years, that was eventually expanded to become that, and that which was that were the same temperature at 400,000 years. But if you look at the size of the universe at 400,000 years and where we are now, the light that's reaching us that we're seeing over here and the light that we're seeing over here, we're not in causal contact yet at 400,000 years after the Big Bang. They shouldn't know they need to be at the same temperature. And you can't get around that in conventional Big Bang. And it's called the horizon problem. And it's truly a causal issue. The uniformity of the Big Bang all the way around causes, it is causally in the Big Bang, we do not know how it could all be at the same temperature. Because you're talking about space that there had not been time for light to reach from one end of the universe to the other at that time. When we look at the Big Bang now. Already talked about the flatness problem. Then there's the large scale problem, which is really in the Big Bang theory in and of itself. We don't know why the temperature is so uniform. how did the structure ever get there? We know we have a non-uniform universe, but there's nothing in the Big Bang theory to give you that. It's uniform expansion of space. Everything is isotropic. So yet we have structure. So you have to have a way of producing the structure that we see in the universe if you're going to have a real cosmology. It turns out that there is a completely wacky way to solve all of these problems, which goes under the name of cosmic inflation. And here are a few of the players. It had been talked about a little bit earlier, but Alan Guth at MIT was the one who really sort of launched this idea. And it's called inflation. And it fixes all of these various ideas. So let me see which slides I took. Okay. So the idea with inflation is that through some mechanism that we don't know, you have a quantum fluctuation in the characteristics of space. And it turns out that you can structure the virtual particles in the vacuum, if you want to think it that way. If you're into string theory, you can structure the way in which the extra dimensions are folded up, such that you have this repulsive term in Einstein's field equations. So you can create, theoretically, ways in which you can make space unstable such that it actually expands at a vast rate, much faster than the speed of light. And speed of light limit is a thing like information transfer, and that's the speed of light. You actually can expand space faster than that. It's not limited. So this may sound completely wacky. I mean, it does. So the idea with inflation is that you have a quantum fluctuation in the structure of space-time or in the types of virtual particles that exist in that whatever was there. And this now expands superluminally very fast, okay? So you can start with an arbitrary geometry of curvature. And now you take this and you expand it really big, and it's just like we're on Earth. It looks locally flat, and yet we know it's not. So inflation, for example, if you take this idea, you have this really fast expansion, and then whatever it is in that model that is causing this repulsive thing decays away. So in string theory, you have the extra dimensions sort of twisted up in a way that they give you this term in the Einstein field equations causing this inflation, and then they decay into they relax into a different state, which is more like a ground state, and that will cause this inflation to stop, this expansion to stop, okay? And so when it stops, the energy that's sort of tied up in this expansion, which is vastly faster than we're currently expanding, is dumped into radiation, which turns into mass. Okay? Now, because you have quantum fluctuations in energy as this thing is expanding, you have non-uniformities in how much energy is placed in place. So when you do that dumping, you basically will have non-uniformities. So all of a sudden, you're answering a lot of things. The flatness of space, because you take something very small that's not flat and you blow it up to be immensely large, and the observable universe is a very small fraction of that, the space will look locally flat to us. Because you have quantum fluctuations in energy as this thing is expanding, they get stretched to cosmic scales. It will literally give you non-uniformities in the energy distribution in the universe that should have, because they continually are formed, you'll have some of them very big, some of them smaller, and they'll give you a power spectrum in sizes of non-uniformities that matches what we see pretty well, which is pretty amazing. You don't really start from nothing. You start from something that's sort of like a quantum fluctuation. You could say, in what? All right, now you're going to get me on really thin ice, because I don't think we really know, but I can give you some pictures, or I can talk a little bit about it. You sort of extrapolate the start. You do sort of have in this, you might have a beginning of time, but there are ways to construct this where you actually don't have a beginning of time. I'll talk about that in a second. So the idea is that we have a period of inflation that lasts from about 10 to the minus 44 seconds after this quantum fluctuation begins to about 10 to the minus 37 seconds. It then basically slows down, dumps the energy into radiation and matter and this primordial soup, and then you map directly onto what we know as the Big Bang model. Okay? And by having that weird thing at the start, you've actually solved the fundamental problems of the Big Bang. You now have, because at this stage, everything is causally connected. You have a period when the whole universe literally knew what temperature it ought to be. And then you expand it. And because you have the quantum fluctuations happening, you get the non-uniformities in. But that part of the Big Bang, that part of the cosmic microwave background, that part need to be at the same temperature, roughly, to within that 1 part in 10 to the 5th. So it explains the horizon problem as well. Okay, so it solves sort of all of these crazy problems. Okay, so just to go on a little bit. The problem with inflation is you don't know how to really stop it anywhere except at a point, because it again has to stop with a quantum fluctuation, a change in the way the space-time is worked, or a change in the nature of the virtual particles in the vacuum, and that happens at a spot, which means I can't have this expanding universe and then stop inflation everywhere. So in fact, if you believe in inflation, and it is somewhat supported, it's not a smoking gun yet, but it is somewhat supported by the data looking at the size of the spots in the Big Bang. If you have it, you also then have multiple universes, because inflation begins, it keeps going, you get it to slow down here, so we form something that looks like an observable universe here, or a region of space that is where inflation slows down, and this may look like our universe, but in the meantime you have this the space inflating everywhere else, and it may stop here, it may stop there, it may stop here, and when it stops, these fluctuations could be a little bit different, which means the physical laws in each of these regions could be a little bit different. But you can think of these as bubble universes, if you will, in this inflating matrix. And you can sort of go back in time, and in a sense, we have something called eternal inflation. One model is that the universe is inflating, or the greater reality is inflating, and out of that pops these bubble universes, of which we are just a small part of one.
Where does the accelerating universe now that we just recently discovered, the dark energy, fit in?
That inflation's going on, the inflation stops, okay, in this certain region. So inflation, and now there is possibly a completely unassociated mechanism which could be very similar to inflation, but its effect is not as big, okay? So the two don't have to be the same sort of thing. I think you can concoct a way for a type of geometry to the space-time, or a type of virtual particle where, we call them fields in field theory. I say we, I don't do this very, it's not my, where things will expand really fast, and then you can fluctuate where things will slow down the expansion here, but it might be that you can construct this to be the same basic mechanism, fine-tuned in a way to do it, but they could also be quite different. So, so we don't know. At any rate, in the inflationary picture, our observable universe is really just a piece of a large portion of a much larger fraction of the great reality, which is larger than our observable universe. So that's a different form of multiverse, which is space-time just like what we see, but it goes much further than we can actually see. And because there's a finite distance, even if you wait forever because of the expanding space, the observable universe will always only see a portion of the expanding reality, because as you go further away, the space is actually moving away from us faster than the speed of light. So there's a finite region of the great reality that we will ever sample. if through inflation or some other mechanism, the great reality is a good bit larger than our observable universe, then there are many portions of the great reality that we will always be causally disconnected from, which is a form of multiple universe as well. That is a region of space that all shares the same physics we do. You have the accelerating expansion, and it's due to some dark energy mechanism that we yet quite understand. Outside of that, there may be this inflating reality that fixes sort of the early Big Bang problem.
I actually understood that.
Oh, good. Yeah.
The other problem, why are we mostly matter and not equally antimatter and matter? Is that speculated on?
We haven't solved it. There's a lot of speculation about it. We have discovered, because in the early universe, if you have energy decaying, you have particles and antiparticles formed, and there should be nothing to break that asymmetry. Okay. It turns out that if you look in gory detail at a very small, at the interactions of quarks, you will find that there are sometimes asymmetries where you have matter interactions and antimatter interactions a little bit different. This was discovered in the 1960s and got a Nobel Prize for Cronin and Fitch. And we call it CP violation. Basically, the quantum numbers CP constitute matter and antimatter symmetry. It turns out people have done very high precision experiments looking at quark CP violation, and it doesn't appear that the asymmetry is large enough to actually create this big, larger asymmetry for the universe. So it turns out that very recently, in fact, we discovered that neutrinos have mass. And if neutrinos have mass, it turns out to open up the possibility that there are differences between how neutrinos and antineutrinos interact as well. And there is a possibility, theoretically, that CP violation exists in that sector, and it's big enough to explain the asymmetry in the universe. There's some big ifs, ands, and buts there. But what was actually an open question until about 2 days ago was whether the way in which the neutrino interact was such that we would ever have a chance of measuring the matter-antimatter asymmetry. And we measured, there was a parameter that was almost measured pre-earthquake by the experiment that I'm on in Japan. We got about a 2.6 sigma measurement, and we published a paper on it, in part because the earthquake came and we weren't going to get data for a year. But another experiment, in fact, just published a 5.2 sigma or whatever, that there's a parameter in the neutrino sector that is big enough that we will be able to do measurements. So right now, the big push to understand that problem is actually neutrino experiments, and it will probably be hard to say, 10 or 20 years before we know that answer, whether it's neutrinos or not. It could be something we totally don't yet have any clues about. But that's sort of where that is right now.
I just wanted to point out, if people are interested in the philosophy of physics and questions like be they metaphysical or about unification or different bents in physics in the past 100, let's say, years, that we're having a philosophy of physics Cracker Barrel at the AAPT meeting in New Orleans. I know it's hard for high school teachers to go to winter meetings, but it's next January. American Association of Physics Teachers is meeting in New Orleans.
And it's New Orleans.
It's New Orleans in the winter. January. Yeah, in January. So just before hurricane season. But I'll be leading that discussion. It'll be an open discussion, so it's a chance for people to come and say what they're interested in.
It's very cool. Well, yeah, once you start talking multiple universes, you get into religion and metaphysics very quickly. And in the book, I mean, I address a lot of these issues. I try not to take sides so much, but do try to lay it out, and there are lots of sources and everything. So it's fun that way. Yeah, we have a physics and philosophy group where we had some fun talking about different forms of multiple universes. I mean, what people are most familiar with is sort of what comes out of quantum mechanics, but this cosmological is a totally thing. That I had a publisher who was trying to get me to write a book about multiple universes. Thinking, what do I know about multiple universes? You know, I've learned a little about quantum mechanics. I think there's something in cosmology, but it wasn't until I started digging into it I realized that there are many different, basically conceptually independent things that can lead to multiple universes. So it actually could be that it's not whether we live in a multiverse, but it's actually how many different kinds of multiverse that we live in, which is bizarre.
So what do you do about this curriculum, about multiple universes for the curriculum for your majors, your physics majors?
Nothing. Isn't that horrible? Nothing. I have them saying, gosh, I wish we could talk about that in our classes. Sorry, you got to learn about WKB approximations, you know, Lagrangians. Yeah. And there is a bit of a reason for it, because I'm hand-waving. I'm not really throwing up Einstein's field equations and doing the field theory. So formally, or the string theory. So formally, the mathematics behind at least the science-inspired multiple universes it is tough, right? So that's part of the problem. Now, a few of them take my class, and you know sometimes we have these conversations, but it's not formal. They might talk a little bit about it in say, their quantum mechanics class. And hopefully they talk a little bit about it in a cosmology class, but by then their cosmology, I'm sure, is like a graduate class.
Because I have this crazy theory, really crazy. But if we offered all of these interesting courses that we offered to non-majors, physics for poets or whatever, if we offered some of that curriculum to majors, it might do something about these different leaky pipelines.
I agree, and I certainly don't stop the scientists coming in and taking my class. But the goals are unfortunately different for our physics majors versus our non-majors, although I agree. We don't, I don't know why I was a physics major or why I went to graduate school in physics, because I don't think I truly began to appreciate how cool it is until I figured out Maxwell's equations and the model for light. And I didn't do that till I don't know, I was a junior in college or something, right? So what possessed me to stick with it, I have no idea. We don't do the fun stuff usually very early. And I know you guys are terrible. I mean, it's even worse, right? Because you not only feel obligated to do stuff, you have the law sitting there telling you, gotta do it a certain way. So, I mean, there's a guy, who unfortunately just died this year. His name was Jack Campmeyer, who maybe you ran across, because he was really a phenomenal person pushing small group learning actually in all areas at U of R. So we have a thing we call our workshop program, which is built on many of the same ideas that physics education pushes. And we used to have these conversations where I would talk about feeling pretty constrained when I was teaching pre-meds, teaching for the MCAT or whatever. And he just, don't feel so constrained. You're there to educate them. They can figure out stuff on the MCAT.
They're going to take the prep course anyway.
Yeah. And so I did find, I feel somewhat constrained teaching physics majors as well, because there are certain things they really need to know when they go into their upper level courses. But it was pretty funny. When I teach the pre-med and I start talking about quarks, I mean, usually when I start electromagnetism or something, I'll talk about fundamental charges and the fact that quarks actually have partial charge. So I'll always go a little bit off the beaten path. But the minute I do, you can fully see 2/3 of the class completely disengaged. You know, the pencils go down, the phone comes out, and that's fine, because I'm actually talking to that other third who get interested in the class for the first time when you actually start talking about some interesting things. But it really scared me when I taught our honors physics class of about 40 students for the first time, because I went off on my standard tangent, and I was, had that little feelings of guilt, when I did it. And I looked up, and they were all on the edge of their seats, and I was like, oh, wow, this is going to be a fun semester. So, I don't know, I totally understand. It's a really hard problem, and I don't really know.
Conversely, from similar viewpoints, we get students come in as freshmen and go, yeah, I want to do some research as a freshman on string theory. They've seen Nova. Right? And the wonderful thing about Nova, it makes that stuff so accessible and so exciting. And then the next step requires so much stuff in between. I don't know how we solve the excitement. Here we actually teach our incoming students a course in special relativity. Because there's no math.
Yeah, that's
other
a
than
great.
algebra.
They love to talk about that.
Yeah, yeah.
And we do push that at early stages in our physics majors classes as well as the non-majors. And yeah, relativity is absolutely wonderful.
Yeah.
People excited about it. I mean, part of it is just who we are, right? I mean, science is really bad about layers and layers of lingo and concepts that are built on things. And we're really bad about forgetting what life was like before we knew that language. I mean, when I find a physics professor at U of R, a science professor, actually, well, it's not just sciences. If you see a bad class, very often it's because the professor or teacher doesn't remember what it was like to not know those things. And whenever I find myself completely disconnecting from the class, what I try to do is to just try to remember what it was like to be their age, which is getting scarier and harder as I get older.
It will get even harder.
I know, it's getting pretty hard now. Yeah. So, but I think that's the important thing to do.
Problem is the education right now, a lot of that stuff has been taken out, especially at our level. It took me 8 years to push through 2 courses for physics for non-majors in our school, physics of sports and physics for art, physics of the arts. And they took 8 years to get them through. We've been teaching for 5 years. People are interested in them. Just got them. Got them. Those kids don't need that. They need, I'm not kidding, the study, the superintendent actually said this, they need more study halls to concentrate on the task for reading, right?
Yeah.